laser cleaner or something. All right, good afternoon, everybody. I'm going to talk today about the variability of noble gas species in the lunar exosphere as were observed by the LADEE neutral mass spectrometer instrument. And first, I would like to acknowledge all my colleagues and the entire LADEE science team who did a really tremendous job in securing this data set and helping in the interpretation of some of the results I will be showing you today. So, as all of you probably know, the LADEE mission ended in mid-April, but during 6 months we, with the neutral mass spectrometer along with the two other instruments, the ultraviolet spectrometer and the dust counter, spent time trying to characterize the exosphere of the moon. The neutral mass spectrometer was designed to survey a large panel of species, but really we wanted to focus mostly on the two noble gases here, argon and helium. These two species were already discovered, and some mapping was done during the Apollo era, and we wanted to really focus on these two because looking at noble gas is really a great way of understanding the basic mechanisms of interaction of the exosphere with the surface, how it gets recycled and how to escape to space. These species don't undergo any chemical reaction, which makes interpretation of the data much, much easier. Okay, so as soon as we pretty much got it and started the science phase of the mission, we were able to very quickly have a sense of what the argon and helium were doing. Here I'm putting some raw data, function of local time on the moon. The sunrise, it's here, that's where the periops of most of the orbits were located. And some counts per second here, which is a proxy of abundance as seen by the instrument in orbit. And you can see here the argon 40 and the helium 4 as mapped during one orbit. But more than helium and argon, we were able to very quickly pick up neon 20. Neon 20 was a surprise because we didn't have much estimates of how much we will be seeing in the lunar exosphere. Neon 20 is not really straightforward in the way in interpretation because it comes as superimposed to other isoporic interferences like doubly ionized CO2, which is an internal contaminant in the instrument. So we had to do a lot of work to basically extract that neon 20, as I will show you a little bit later. Okay, so helium was really the first noble gas we focused on, and that's starting from the commissioning orbit. Actually, during the commissioning orbit, we had the opportunity as part of, while we were commissioning the instrument, to take very interesting data sets on helium. And this data set is really unique from all the rest of the data we took for the rest of the mission. And the reason is that during commissioning, we were in a quasi-circular orbit, 250 kilometer altitude, which actually allow us to get away from the convolution between altitude and abundance as seen by the spacecraft in orbit. As you all know, if you measuring a varying abundance around the moon, while your altitude of the spacecraft is also changing, it makes it a little bit harder to decouple what's actually variation of the exosphere versus what's due to the change of altitude. So during commissioning, we didn't have to deal with that. The project gave us a nice circular orbit, and the data basically we measured were purely variation of the helium exosphere, purely the diurnal variation of the helium exosphere. The second reason why this data set is very, very interesting is we took it over about a span of 2-3 weeks, And we had some of the data we took were done while the moon was in the plasma sheet, so in the magnetotail, and the rest were a few days after as the moon exited to the solar wind. And we could see right away how basically the helium depletes as the moon gets into the magnetotail and then recovers slowly as the solar wind resumes its presence as an input to the lunar exosphere, and we get to a maximum in pretty much in 5 or 6 days after we exit the magnetotail. So we kept doing these type of measurements for pretty much the entire mission. For helium and argon, we tried to secure at least a measurement of argon or helium every 12 hours, but actually we ended up doing much, much better. We actually got to an average of 4 hours. We measured over all local times the abundance of argon and helium every pretty much 4 hours. And here I'm plotting the data. You may have seen this presented yesterday by Jasper Halikas, who really helped a lot in correlating this data. You see here the helium above the sunrise as function of day of the year and reduced to the surface abundance using an average scale height. And the black dots are the NMS data, and you see there's variation with the days. Here are regions where the moon is in the solar wind, and you see in green, what seems to be green, is the period where the moon is in the magnetotail. And we can see that there is quite a bit of variation and always a nice decay while the moon was in the magnetotail, and that happens, we saw that over multiple lunations. And Jasper was very helpful in getting us the alpha particle flux and running this correlation analysis between the integrated flux, alpha flux as a proxy for protons, and with the NMS data. And you can see that we have an excellent correlation with a 4-day exponential running decay. And more than that, we actually, if we go and plot in every time we had reported CME observed on the Earth map, on Earth, you can see that we can actually correlate most of the big jumps like this one or this one to actually big CMEs or fast flows coming from the sun. So in order to look at spatial variation or diurnal variation of the moon, we had to correct for this actually temporal variation. So we take this map and we correct all our data by scaling everything to the maximum observed abundance. And by doing that, we can actually derive a scale height temperature, mostly on the night side of the moon, because that's where we have the highest signal of helium, and surface abundance. And you can see that basically the derived scale height temperature maps pretty well the surface temperature, which is in black here, assuming a running average of 6 hours. I mean, at around midnight, they're very close. And then as you go toward the day, the scale height temperature rises a little bit faster than the surface temperature. And by using this scale height, we can reduce all the data to the surface. And you can see that the helium pretty much follows the classical T to the 5/2 law of exospheric equilibrium for gases that don't condense at the surface, and with the peak that happens slightly past midnight because the minimum scale height temperature is right there at 1 a.m. local time. We looked at neon and we tried to look at any temporal variability. We didn't expect to see any because the neon photoionization lifetime counts in months, and thermal escape is in years. So the neon should be a very stable reservoir, and we couldn't discern any temporal variation that's more than the actual statistical noise in the measurement. So if we did the same job with neon, we took all the data set, we reduced the data set to the surface, we derived the scale height temperature, and you can see here that the derived scale height temperature pretty much follows the surface temperature. Neon is locally accommodated to to surface beneath, and the minimum scale height temperature happens shortly before sunrise, and that's where you will see the peak of the neon abundance at the surface, just around 5 a.m. local time, 1 hour before sunrise. We also were able to measure neon 20 to neon 22 isotope ratio. We were able to do that toward the end of the mission, where the altitude of the spacecraft was really low from the surface, and we had a good measurements of neon 22 isotope, and basically the average value from that data set points to the same value that SOL measured for the solar wind, or the values we measured from lunar rock samples that were returned to Earth. So pretty much all the neon we observe is of solar wind origin, which that's what we expected. Argon. Argon was really a very interesting measurement to do. The results we got were very exciting and at the same time very puzzling. And the reason is, can be seen here, for example, is when you try to, if you assume that your exosphere, it's a simple pressure law, and you try to plot your scale, your altitude versus your log abundance, you expect the data to fall on a nice scale height line, and that's pretty much true for local time 11 a.m., 9 a.m. But as soon as you start getting towards sunrise, the data becomes really chaotic, and it's very hard to find a single scale height that explains all the data. I colored here the data by selenographic longitude. You can see that actually they're grouped. You can derive a scale height per a group of selenographic longitude, but you cannot just have a single scale height for all selenographic longitude as we did for helium and neon. So right there we were suspecting that something not really simple was happening with argon, and we needed to look further into the data. If we take the data, if we take the data set and we just average it and try to reduce the data to the surface, the abundance to the surface, using a simple scale height model, we found that we actually can reproduce very well the sunrise bulge that was observed by LACE in Apollo 17, but the way the argon trails after sunrise toward noon really did not match what we expected from a simple Monte Carlo model. This model was initially initiated by Hodges, but was actually confirmed again by many other teams. So our argon was pretty much at noon was about almost an order of magnitude higher of what you expect from a simple uniform accommodation model. So we start looking a little deeper to how the argon actually behaved, and we try to plot these data in a different ways and try to see correlations. And actually, if you try to plot all the data that were taken at the given local time, let's say here, for example, at 4 a.m. local time, 2 hours prior to sunrise, and plot them for all the lunations. We had about 4 lunations during the mission, and for all selenographic longitude, we discovered there was actually a bulge around minus 50 degree, about 50 degree west, which correspond to the western Maria. And that bulge actually sustained itself at all local times. It's you can see it here half an hour before sunrise. It's still there, And even 1 hour or 2 hours after sunrise, you can still see it here. It's not as prominent because we're on a log scale, but if you plot it in a linear scale, you'll see at least a factor of 2 bulge in around minus 50 degrees longitude. And you can see actually it repeats itself. So if you plot all the data from all lunations, they're 30 days apart, you get that bulge at all local times at the same manner. Another way to look at it is if you plot a data taken in one orbit for let's say for a given day of the year, you plot them with a function of local time, we could see like actually there are superimposed to the classical curve of freezing, sunrise desorption, distribution, and the bulge at, here you see the bulge at sunset and then refreezing. We see actually that there is a local bulge that keeps moving as with day of the year. So you see it here, the peak is here, then it moves as the terrain, the 50 degrees, minus 50 degrees longitude moves with local time. You see it moving to basically a couple hours before sunrise, and then it moves here, and then it actually even increases the sunrise bulge that we observed, and just the terrain after it, actually it's a minimum, and as we move, that minimum keeps moving. So basically this area here, on the lunar terrain, the western area, is actually what's driving this bulge, and this bulge actually rotates as the moon rotates around itself. So the first idea that came to mind of why we have a bulge of argon around the western areas is actually came from the potassium distribution of the moon. These maps from Lunar Prospector and Kaguya, and more recently from the Cheney probes, show that there is an area of increase of potassium-40, the Pusillanimum creep terrain, that actually have almost 2 orders of magnitude increase of potassium-40, which is radiogenic and decays into argon-40. So we thought that may be actually a source of this argon bulge, and as this terrain moves in local time, this argon bulge follow it. This may be actually a part of the answer. I'm not sure this is the total answer. We think it's still there is some also thing related to how the argon accommodate with that specific terrain compared to the highlands, for example, that may play a role in enhancing this argon over all local times and by the same order of magnitude. So other than the temporal variability we saw in argon and the spatial diurnal variability, we also were able to pick up some what we think is a long-term argon variability that may be pointing to a venting event. So here, for example, I'm plotting all the data taken at the same local time, 10 a.m., about 4 hours after sunrise. And the color code is basically the selenographic longitude. And you can see as terrain moves at the same local time, we get that creep area argon bulge, which you see that's around minus 50 longitude. So we get it every lunation, and then it drops back down. But when you plot the data, you actually see there is actually a long-term variation, even of how high the peak or the trough of this curve are. And if we do that exercise for multiple local times and at different longitude, like I did here, I took about a dozen of them, you can actually, they all follow the same curve, a normalized curve, and we can see basically that over the 6 months of the LADEE mission, the argon seems to have increased about 30%, and then dropped in a couple months to about by 20%, and leveled off. And actually, it seems we didn't have enough data, but maybe the trend was again about to go up again. And while this actually was exciting, actually we found another observation that was done by late in 1973 also that shows that what they suspected to be a venting event of argon back then, with argon actually having a time constant of about 50 days. Here, the time constant is much faster, it's about 15 days, which is right what the photoionization lifetime is of argon. And so we think it's actually a venting event where the source completely, the vented shut down suddenly, and we basically, photoionization took over and got rid of the excess of argon in the exosphere. So to summarize, we really took a very comprehensive data set of light noble gases, helium, neon, and argon. Helium and neon show temporal variation, at least for helium, and we have isotopic ratio for neon that are indicative that both these species are pretty much solely of solar wind origin. We couldn't pick up any signature of endogenic helium in the exosphere. If it's there, it should be, it's probably at a very low abundance. The argon exhibit local time abundance enhancement localized over the western areas. We're not sure actually what the full mechanism that actually creating this bulge. It can be the fact of the presence of high abundance of potassium 40 coupled with the nature of the terrain itself makes it that there is a bulge there. And also we think that we have observed what we can be characterized as a venting event with a large time scale decay of argon afterward. That will be all. Thank you.
Thank you. We may have time for one question while we're preparing the next speaker. Please make sure you have a mic first. All right. Well, thank you very much.